Didn't want to run it too long, so I stopped, and this is part two. So we've been talking about how Pascal's triangle has some interesting patterns. We've been talking about the rows in Pascal's triangle, the sum of the coefficients in Pascal's triangle. And what we've come to recognize is that the sum of the coefficients in the expansion of an x plus y to the n on Pascal's triangle is always 2 to the n. So the sum of the numbers in the n plus 1th row of Pascal's triangle is 2 to the n. You've got to watch how the row number is related to the number of possibilities. So row 5 deals with 4 binomials. Row 7 deals with 6 binomials. Technically, row 7 is the result of x plus y to the 6. And here I'm looking at the last one as x plus y to the n. So I don't have a row reference, I've just got a power reference. So my exponent reference is going to be my answer for my 2 to the n. So we've already done a lot of work with this. You can add your exponents and see that patterning, but we'll try some problems below. So if I'm in the 10th row of Pascal's triangle, my pattern of 2 references 2 to the 9. If I'm looking at m plus n to the 12, I'm not talking about rows. I can simply find the sum of the coefficients by going 2 to the 9 or 2 to the 12. So we'll calculate that. Now, question C I find a little bit deceptive. Question C is talking about an expansion of x plus y to the 15, and it asks me to sum up all of the values of 15 choose 0 all the way through to the end 15 choose 15. That would be the complete row. So I can figure out that sum by going 2 to the 15. But the second one is a little bit deceptive. It starts at 6 choose 0, 6 choose 1, 6 choose 2, plus dot, 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 etc. Up until only 6 choose 5. You'll notice that it does not include 6 choose 6. So I'm missing the last term. Well, what's that last term? That last term we know is a 1. So you could go 2 exponent 6 minus 1, or 2 exponent 6 minus 6 choose 6, which is also equal to 1, by the way. But 2 to the exponent 6 minus 1 is 63 if we were summing those coefficients. Now, why did I need more room or more memory space for my videos? We're going to go back to our root problem, path problem. How many different ways can I get from A to B if I must always move closer to A and B? We looked at it as a choices opportunity. We've solved it already, and we actually solved it with Pascal's triangle in mind. And that's by changing the orientation of the diagram a little bit. This is A and this is B, and I'm going to number my vertices. How many different ways can I get from A to this vertex? It's 1. Well, if I keep going along the outside, it's 1, 1, 1. But what about the number of ways of going here? That's 2, 3, 3. What's this vertex going to be? A 4 and a 6. By the time I get to B, there are 10 paths, which is a question we answered earlier in this unit. And looking at the path method was one way of arranging. Remember, one of the kids had considered arranging it as 3 easts, east, 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 and 2 souths. How many different ways can you arrange that? And that gave us the 5 factorial divide by 3 e's and 2 s's. But we're going to use this Pascal's triangle or vertex method to solve some more. So can you try out the vertex numbering system of going from the bus station to the concert hall by counting your vertices, by counting your paths? I'm going to give you a little bit of time to do that. I'm going to throw on all my ones, but my middle numbers we'll have to figure out together. So I started with my outside, like the outside of Pascal's triangle are all ones. Well, how many different ways can I get to this spot? That would be a 2. And then this would be a 1 plus a 2, which is a 3. And this would be a 3 plus a 1, which is a 4. So 1 plus 2 is 3. 3 plus 3 is 6. 6 plus 4 is 10. So Pascal's triangle just coming at us sideways. 4, 10, 20, 5, 15, 35. Now that 35 goes into this bottom square, and I don't have any choices of moving down, so I've got 35s which form the bases of my outside, like the 1s form my bases of my triangle for Pascal, 35, 35. And now I have to work that inside. So the inside is going to be Pascal's triangle getting really big. 35 plus 35 is 70, and 70 plus 35 is 105 for that location. 70 plus 35 again is 105 for this location. And to get to the concert hall is 210. I find this a really nice visual way to track. I would encourage you to try your pathway diagrams in this method. And we've got one more, same kind of operation. Start off at the train station, 1, 1, 1, 1, 1, 1, 1. But then I get 2, 3, 4, 3, 6, 10. What's on that? On that corner, you would get another 4 because there's no other ways of getting there, which gives me a 14 for here. So 4, 10, 20, 34, 5, 15, 35. 35 plus 34 is 79. Kind of seems like an odd number. 69, pardon me. 69. And then I have to come to this spot here. What happens to get to this spot there? Any changes? No changes to get to that spot. So it's 15 to that bottom corner. Then 15 plus 35 is 50. And then 50 plus 69 is 119 different ways to get down to that corner. Well, I hope you like that. There's one other application of Pascal's triangle, and we'll try that this week as well.